Hey, I'm Dave. Welcome to my shop. We're not actually going to be in the shop today. We're going to instead head into the Oval Office and take a look at the source code for my ESP32 single-chip spectrum analyzer. I'll take you on a tour of the major software building blocks that come together to form the spectrum analyzer, and then we'll dive right in and look at the details of some of the more interesting pieces of code. If you're a programmer, I think you'll find the tour interesting. But even if you're not, and the code itself looks as though it were entirely written in Greek, that's okay too, because you'll still get a bird's eye view of how everything works. There used to be a PBS series called The Operation that documented complicated surgeries, and I always enjoyed that show, even though I am certainly not a surgeon. I hope you'll enjoy the code in a similar fashion. But before we get that view of the code, let's do a hand-wavy overview of what's actually going on with this thing. First, there's a Y splitter on the headphone jack of my Mac Mini that routes audio information to the spectrum analyzer circuit. And by the way, there's no reason that the audio source needs to be a Mac. That's just what's on my bench. It could be a Sony Walkman if you wanted. There's an audio input jack on the breadboard, and the tip from the audio cable goes right to pin 2 of the ESP32 chip. Thousands of times every second, the ESP32 will stop whatever it's doing, take a look at the audio that's coming from the stereo, and sample it with a call to analog read, saving that value away in a buffer. One of the CPU cores on the chip is constantly waiting for the music to be read, and about 50 times a second, it takes all the samples that have accumulated and runs a special math procedure over them, including what's known as an FFT, and out magically pops a set of peaks for each of our spectrum analyzer bands. The other core of the CPU spins in a loop drawing those results. Put it all together and out pops a fancy display to impress your friends. It's just that easy. So let's get busy and write some code. Alright, here we are in the Oval Office. We're looking at some code. And yes, I really do live in the big white house with an Oval Office, but not that one. We're going to look at my ESP32 single-chip spectrum analyzer and the source code that drives it. And so lest it bother you, I will spend my time looking up at the monitor, which is where you will be looking too, and so we're both looking in the same direction, and so that's why I've got the camera set up this way. I've seen other people do it, and it seems to work out pretty well. So let's give it a shot. So I believe I set out in the shop that there were 4 main sections of code that you had to be concerned with if you want to follow along. And those are, from top to bottom, the sample buffer. These are flat buffers of 512 little samples read from analog read into memory and passed, whenever 512 of them are accumulated, off to the sound analyzer. It runs an FFT and some other math on those samples to produce a set of peaks in each of the bands. That is in turn handed to the spectrum display class, which draws those peaks as bars and does the decay and the little white lines and so on. And it does all that using the LED matrix graphics class, which is our class for drawing primitives, lines, text, and so on the LED panels. Those 4 pieces are what it takes to make up the spectrum analyzer. So the first of those, the sample buffer, is, as we said, it's a buffer of n samples, and n has to be a power of 2 just because of the way the FFT math works. 512 seems to be about right for our purposes. And so, about 50 times a second then, the sample buffer fills up with its 512 samples and is handed off to the sound analyzer class. This takes the sound buffer as an input, runs the FFT and some other scaling math upon it, and out pops a set of band peaks as its output. The spectrum display knows nothing about music or audio or math. It just knows how to draw the band peaks that come out of the FFT in the sound analyzer. As the sound analyzer produces packets of these completed peaks, it draws the bars and the little white highlights and then slowly decays the bars and does everything else that's related to the visuals of the display. And so here are your 4 conceptual pieces arranged on screen. The interrupt service routine, or ISR, samples the audio and fills sample buffers that are passed to the sound analyzer, which produces a set of band peaks for the spectrum display to render. Whatever idle cycles are left over are used by a little TFT display to display some status and statistics to the user or developer. And finally, you might be concerned whether a little microcontroller can really do all this work and service interrupts this quickly, all while doing floating point math full time and drawing the LEDs. Rest assured, as you can see from this little graph I've assembled, the ESP32 is many times faster than the Arduino Uno and similar chips, and it does have floating point math support right on board that we use sparingly but appreciatively. Okay, so here we are confronted with the blank canvas of Visual Studio 2018. What else do I have installed to make my setup work that yours, of course, will not have? The first is Visual Micro. That is, they have an evaluation version and a commercial version, and you can use that as well as the Arduino IDE. So I have those 2 installed, and the Visual Micro IDE actually depends on the Arduino IDE. So you need both if you're going to use the latter. Okay, our next step is File New Arduino Project. We'll call it Spectrum Analyzer. let it churn away. There's our file, and we'll strip out everything except the very bare two functions. And so with just the very bare basic setup and loop, let's compile it and make sure that it does in fact compile. Which it does, and that's all we need. Now we can start adding. Okay, as we get ready to code, we'll just take
perimeter motion northwest 3.
Anyway, as we get ready to code, the first thing we need to do are add the libraries that we need. So that will in turn add a whole bunch of header files that we're going to strip back out to the bare minimum. So let's go through and add the libraries. The first is the Adafruit graphics library. Second is Arduino FFT. The third library is Fast LED. Oops, it's going to churn away there for a second. And the final one, UHE2. And look at all these monstrous headers. Strip them back out, and in a second we'll add back in just the ones we need. But going through this process adds the library references for link time, and that's what we needed to do. And that's why we needed to go through those steps, even though we're going to set up the header files manually. Okay, how are we going to build this file? What are we going to add to it? Well, first we're going to put in some kind of descriptive header. We're going to put in our include files, our pound defines and other definitions, our constants, our variables, our complex objects, structures, and so on. Setup and loop, which we already have. Then we need three main functions. TFT update loop, and that's what happens on idle time. Sampler loop, that processes the audio, and matrix loop. That's what draws the display. And once we fill out all these pieces, that's going to be our project. So that's our roadmap. Now, I'm not going to force you to sit here and watch me type at length, because I can't type when being watched, and being recorded is about the same as being watched. So bang, there's my header. Because I pre-typed it for you. That's just the kind of guy I am. I will, however, update the date. And we'll update the comment to YouTube. There we go. Okay, our include files, I simplified down to this set of about 6 files. One thing I'm going to do is, before we include anything, I'm going to pound define fast LED internal, which is a symbol that if you define, quiets the fast LED build, which otherwise prints banners and is otherwise very proud of itself for compiling, which I don't really need. So I define that and turn that off. For our definitions, we have the following. And these are things that we define at compile time rather than at runtime, such as the number of bands, which could be 8, 16, 24, or 32, but cannot change at runtime, only at compile time. Same with the width and the height and those kind of features. They are not going to change during the run of the program, just at compile time. And so they are in this definition section. One extra thing I like to throw in all my fast LED projects are some color definitions, because it's 565 color space or 16-bit, and I can't do that in my head as easily, so I've defined the common colors, which makes it a little easier to use. Next, our global variables. And these are all volatile. And the reason these are global and volatile is not because I'm lazy, necessarily, but because these are one layer of indirection between my interrupt routine and my main core code. And these are also things that are modified under interrupt, which is why they're marked as volatile. And for those of you that have never used it or are not sure what that means, what it means is the code that is running in line in the other CPU cores that is not running under interrupt can't assume that the value in the variable stays the same from one instruction to the next. So if it needs to go back and look at the value, it can't cache it in a register or hold it any other way. It needs to go back and actually look at the memory address every time, because the interrupt could be changing it without letting it know. And that's what volatile means. It means, compiler, don't assume, always go look at the memory address every time you want the value. At this point, I'm going to insert includes for files that we have not written yet. That's why you're going to get the red squiggly line. I'm also going to try and zoom in a little bit here to make the font bigger for everybody's ease. There we go. And I can zoom back out when we want to see the overview of what the file looks like, and zoom in for better legibility. There we go. Now these are files that we're going to write. Utilities, the LED matrix graphics interface, some palette code, which is really just color definitions, the spectrum display, and the sound analyzer being the two big ones. Next are our global scope singleton objects. These are things that provide functionality or represent big pieces of code. So we have the UHE2 object for the TFT display. We have our not yet written LED matrix graphics. We have our not yet written spectrum display and our not yet written sound analyzer. Now we need to flesh out and complete our chip setup. This is the standard function that is provided in every Arduino app, and it's up to you to fill it out with whatever your chip setup requires. In our case, we're going to print a little banner, set the serial port speed, and set the pin mode on some of our input knobs. That's our first steps. Next, we'll set up the DAC, and this started out as some sample code, which I'm going to later revise because it has hard-coded output of what the banner displays here versus what's actually passed to the chip. So they really should be in sync, and so I'll make that change later. But the meat of it is that we're setting it to 12-bit resolution. That means every sample, when we read analog read off the audio pin, depending how loud the volume is at any one little moment in time, the number that comes back will be 0 through 4095, or 12 bits, which is the width. And it's going to cycle for 32, or it's going to sample, pardon me, for 32 cycles each time. And it will take super samples, number of samples, which is going to be 2. The clock divisor remains at 1, and we set the pin attenuation to 11 dB for all the pins, which are the input knobs, except the audio input pin, which we put at 2.5 dB. And I'd like to tell you there's a scientific reason why, but of the options available, it worked the best for line level audio, so that's why I picked it. Now, before we continue this setup, I'm going to jump ahead and show you what the loop function looks like. This is where you would normally find all of your functionality in an Arduino app. And our functionality is going to be wait for some huge amount, like 20 years, to only come back and wait again for another 20 years. In other words, the actual loop is going to do no work whatsoever and just remain everything idle. And so the only work that's going to get done is going to be scheduled in tasks, which we'll see back in the setup, because that's where we're going to set them up. So back to our setup, this is where we're going to create the actual tasks. The FreeRTOS operating, it's not an operating system really, it's a kernel. The FreeRTOS scheduler will run tasks for us. We're going to create 3 of them, and so each one gets a task handle. Sampler task is going to be our audio sampling. Matrix task is our matrix LED drawing, and UI task is our idle time updating of the TFT display. So the first 2 we create with calls to create pinned to core, or task create pinned to core, which, as you might guess, creates a task and pins it to one of the CPU cores. In this case, sampler task will get put on CPU core 0, and matrix will run on CPU core 1. We haven't written those functions yet, and that's why they are not defined. And so finally, the last thing we have to do is schedule the idle task. I'm going to move this up a little bit. So we create a task pinned to the core for the sampler and for the matrix, and we do create a task for the TFT update loop, but we don't pin it to a core. We'll let it run wherever it's going to have available cycles to run. And we know that that's pretty much only when we actually call delay is going to be the only free cycles left in the system. But we're not going to constrain it to have affinity for any one core. The very last thing that we do in the setup is to start our interrupts, and we'll see that in the sound analyzer when we get to that code, but this is where they're launched. And from this point forward, the interrupts are always running on the CPU. So let's take a step back here. I'll zoom way back out so we can see our code. This is your setup. Here's all our defines up top, the setup code we wrote, and the loop, the work code, which does nothing yet. So it's up to us to fill out these 3 functions as the next step. The TFT update loop is the most mundane of these, so let's just blast it in there and I'll just show you what it does. It creates a little text buffer, and I don't have character safe ones, so I'm guessing at 32. I don't like it any more than you do, but until the Arduino or I do character safe versions of all these functions, I don't have that flexibility. So we're just going to assume that 32 is big enough for these little numbers, which it should be. And it is doing a sprintf into a buffer, displaying the number of frames per second of the matrix and of the FFT, and it's just showing our gain, which is the level of amplification for scaling to the display. So a louder signal gets scaled down more. Brightness is how bright the LEDs are. IRQ hits is an interesting statistic. That is, every time the IRQ is fired, it tries to save the sample into the buffer for the sound analyzer. And if it is successful, it's called a hit, and otherwise it's a leak or a loss. And so it keeps track of those, and with the system in its current incarnation, runs at 99 to 100% efficiency, and all audio is processed. Color speed is the rotation speed of the color palette of the color bars in the graphic display. Once we've assembled all that, we send the buffer off to the UHE2 display, and it runs very slowly, but it updates every couple of seconds. Now, you might think the sampler is actually complicated, but it's the smallest and the simplest of the main pieces of work. All it does is calculate its frames per second based on how often it gets called. It gets the peaks from the analyzer by running a sampler pass. So basically it says, go and sample audio and give me back some peaks. Take those peaks and pass them to the display, and just do that in a loop in perpetuity with a little delay in here to give the TFT 5 milliseconds worth of free time, which is about all we can spare, and that syncs our two workpieces together at about the same progress rate. So I found that if I have about 5 extra milliseconds to waste here, so I let the TFT have that. And finally the matrix loop, which handles the drawing of the LEDs. I'll start from the beginning with this one. It also calculates its frames per second, and it starts by filling the matrix with black, as you might expect. Color speed is the speed at which the color palette rotates, as we discussed, and if it is close to 0, we always draw it with the color palette anchored to the bottom left. And you'll see why when you see the palettes for things like flags. You don't want a flag half scrolled. And for that reason, if it is not scrolling, we just anchor it to the left. If it is scrolling, it gets a fractional amount added to its color based on the number of seconds elapsed, which is a floating point variable, times the color speed. And so if this function is called more often, this will be smaller. If it's called less often, it will be larger. And the net effect is that it will always shift by the same amount based on time rather than how often the function is called. From there, the matrix is turned on, the brightness is set, and it's showing. We do a yield so that the watchdog knows we're alive, and we repeat. Oh, the watchdog is worth a mention. The ESP32 has a watchdog that watches your chip to make sure that you occasionally, which means very often, call yield, which signifies to the chip that you're still alive and yielding your priority to the chip so that it can get the work done. And if you never do that, it will reboot you. And so we make sure that as part of our doing business, each frame we call yield so the chip knows we're still up and alive. One other minor note here is this pound defined turned off right now on screen FPS. This is if you don't want the TFT to be involved, you could comment that out and you can actually draw the frames per second using text on the actual LED matrix display, which takes almost no time and therefore does not skew your statistics when you want to know how fast it really is. Or if you don't have a TFT display on your ESP32 chip and you desperately need to see your frames per second count, you can just enable this. Okay, and finally here is our entire main file. You can zoom in and just take a quick scroll through again. We have our header, includes, defines, our variables, our header files included, our global objects, setting up the chip, which means setting up the DAC, creating the tasks to do the work, and starting the interrupts, the loop, which does nothing, and the TFT update loop, which displays statistics on the chip, the sampler loop, which grabs the audio, and the matrix loop, which displays it. Now, as you recall, we added references to some header files that we have not yet created. The first being utilities. So let's add a new header file called utilities. You want header file. Okay, the first thing we're going to define in our little utility function are are some macros that I find handy. Array size to tell me how big a C object like a C string is in characters, and without depending on the byte size. So if you had an array of 16 bits or 32 bits, you don't want the byte size, you want the array size, and that's what this macro gives you. Period from frequency and frequency from period are just going back and forth from microseconds to times, or hertz, I guess, times per second. And there's really only two functions in here, so it could have been stuck in the main file, but it's a little cleaner out here. One is map float. This is just a version of the standard map function that's used frequently on Arduino, but this handles floats. So given a value x that can range from the minimum to the maximum, it produces an output value from the output minimum to the output maximum. So let's say this went from 1 to 10, and this went from 1 to 100. If you passed it 5, it would produce 50. So it basically gives you the output range in the same proportion as your input value to the input range. Hope that makes sense. FPS takes the duration in milliseconds that it took for the function. You give it the start and the end time, and it tells you how many frames per second that it ran. It caps at 999 because that's fast enough for most use. My initial plan was to do this all in one segment, but even at the accelerated pace, it looks like I should likely break this up into smaller chunks. If this were a professional code review of real production code where I expected you to find my bugs for me, we'd be going through it line by line, but that's not the goal. I just want to give you a sense of how the code works. But even though we're skimming over a lot of the details, it looks like it would be prudent to split it up into 20-minute bites, so that's what I'm going to do. If you found it at all interesting or entertaining, be sure to check out part 2, where the next step is to look at the LED Matrix Graphics class that does the actual drawing of pixels, lines, text, and other primitives on our LED panels. And before this video wraps up, be sure to click the like button if you did, in fact, like the video. There aren't a lot of code review videos out there, and I'm imagining the audience is small, so please be vocal if you are out there, so I know there's an appetite for these kind of technical details, let's say. So thanks for hanging in there with me, and I'll see you in part 2.